So let us start. Last time, if you remember, we were discussing that. So we were discussing this fact in the last class. So this was the fact that we were discussing. If M dash is a submodule of M, and dash is a submodule of N, X belongs to M dash, Y belongs to N dash. Then X tensor Y may have different properties as an element of M tensor product N, or as an element of M dash tensor product N dash. Our ring A, both are A modules. So we took this example in order to elaborate this fact. So we take A equal to the ring of integers Z, M also as Z as a Z module, M dash equal to 2Z as a Z module, and N equal to N dash equal to Z2. Okay. So then this M tensor product N is actually Z tensor product Z2, and M dash tensor product N dash our Z. Okay, is actually 2Z tensor product Z2. And if you take 2 tensor 1 as element of Z tensor product Z2 over Z, then this 2 tensor 1 you can write it as you can write this 2 tensor 1 as 1 plus 1 tensor 1, and then you can put it as 1 tensor 1. So 1 times 1 tensor 1 plus 1 times 1 tensor 1. And again you can put it as 1 tensor 1 plus 1, which is 1 tensor 2, and in Z2 it is equal to 1 tensor 0. 1 tensor 0 is 0. Okay. So as an element of Z tensor product Z2, this 2 tensor 1 is 0. However, but as an element of this M dash tensor product N dash, our A, that is this 2Z tensor product Z2 our Z. This 2 tensor 1 is not equal to 0 because of the following fact. As our claim is that this module 2Z tensor product Z2, it is generated by 2 tensor 1. And because we proven in the last class, if you remember, if mi I and I, they generate M, and J and J, they generate N, and then this Mi tensor Nj, these elements, they generate M tensor product N. So here 2 generates 2Z, and this 1 generates Z2. So therefore you have this. This is because 2Z is generated by 2 and Z2 is generated by 1. So therefore it is generated by this element, these type of tensors. Now if this 2 tensor is 0, then this whole module would become 0. And if 2 tensor 1 is 0, then the whole module 2Z tensor product Z2 would be 0. But our claim is that this module is non-zero. So we claim that this module 2Z tensor product Z2, this is not equal to 0. For this to be non-zero, you define, now Z2, we know Z2 has only two clauses, two elements, 0 bar and 1 bar. So we define f from 2Z cross Z2 to Z2 by f of x comma y bar. Y bar means element of Z2. Y bar is either 0 bar or 1 bar. So we define it by f of x comma y bar equal to xy whole bar divided by 2. We define this map. For all x belonging to 2Z, y belonging to 0 and 1. Okay. Then you can easily check that Z is bilinear, or this f is bilinear. Then f is easily seen to be a bilinear map. Okay, you can just verify it, because if you take x1 plus x2 if you take f of x1 plus x2 comma y, then it would be x1 plus x2 y whole bar by 2. But we know that this bar preserves both addition and multiplication. So bar, so you can write it as x1 y bar plus x2 y bar by 2. And again it is x1 y bar y whole bar by 2 plus x2 y whole bar by. Okay, so likewise the other things. So just verify it that this is a bilinear. Once f is bilinear, then you have here z2 cross, sorry, you have here 2z cross z2 to z2. This is your f, and say this map, the bilinear map of the tensor product is G. 2z cross this tensor product z2, this map is G. Then by the defining property we have we have a unique homomorphism f dash. So by definition of tensor product, definition of tensor product, by definition of tensor product, by definition of tensor product, there exists a unique homomorphism. There exists a unique homomorphism f dash from z tensor this 2z tensor product z2 to z2, which makes the above diagram commute, which makes the above diagram commute. That is, you have here f dash composition G is f. Now, moreover, this f is onto. This mapping f is onto. Once f is onto, so therefore this composition is also onto. Moreover, f is onto. Means Z2 has only two elements. You have 0 bar and 1 bar, you know. So 0 bar has its pre-image and 1 bar also has its pre-image. What is the image of pre-image of 0 bar? Sorry, 1 bar. If you take the pre-image of 1 bar, pre-image of 1 bar are elements of the form this f of 2x y bar, which is equal to, by definition, 2xy whole bar by 2, where you take my x is in 2z, नहीं x आपका z में है, x तो z में है, so x, you take x here as these type of elements 3 5 7 so on, means x you take odd integers, odd positive integers, and you take y as 1. जब आप यहाँ x को फॉर एग्जांपल 3 रखेंगे तो ये क्या हो जाएगा 3 6, so 1 minute, हाँ x को 3 रखेंगे ये 6 हो जाएगा 6, ये ठीक है. अगर x आपको फॉर एग्जांपल इफ यू टेक x here as 3 and y 1, तो दैट वुड बी 6, 6 डिवाइडेड बाय 2, ये हो जाएगा आपका 3 बार, है ना. बट इन z2 3 बार इज सेम एज 1 बार. So you are getting it as 1 bar. Okay. And likewise, if you put 5 and then again you will get 1 bar. If you put 7, so on, you will get 1 bar. So what I want to say that 1 bar has its pre-image elements of this type, 2x comma y bar, where x is running over these and y is 1. Likewise, if you want to take the pre-image of 0, 0 bar would be actually f of 2x comma y bar, where y is again 1 and x you take the positive and the even positive integers 2, 4, 6, so on. So therefore this f is onto. Once f is onto, so therefore this composition is onto. So this means f dash composition G is onto. So this actually implies that f dash is onto. F dash is, so this homomorphism is onto. Okay. So this homomorphism is onto. Okay. So once if this module is 0, then Z2 has to be 0 because this homomorphism is onto. Okay. Now if twice Z tensor product Z2 is 0, then Z2 is 0. This is because F is onto. Z2 is not the 0 module. We know this. Contradicting that Z2 is a 0. Contradicting as Z2 is a non-zero module. Okay, so we are done. Our claim is true. So therefore, as an element of M dash tensor product N dash, that is 2Z tensor product Z2, this 2 tensor 1 is a non-zero element. So this was one of the unique properties of the tensors, these monomial. Now I am leaving some exercises for you to verify. So exercises. First one. If m equal to n equal to this fx polynomial ring over a field, where f is a field, where f is a, we know that this fx is an f module, in fact f vector space, then fx is an f vector space. So you find the tensor product of this m tensor product n over f. So find, okay, so this is the first thing. Secondly, find, so first is Zn tensor product Q over Z, okay, where 0 less than n belonging to Z, means n is positive here. Secondly, you find this one, Zn tensor product quotient module Q by Z over Z. Again here 0 less than n belonging to that. And thirdly, you also find this tensor product Q, tensor product Q over Z. Q is a Z module, so you can think of finding this. And last one, so third exercise, prove that for any A module, M, A tensor product M over A, it is isomorphic to M. Okay, so as an A module, these are isomorphic. So these are three exercises left for you. This one, and this one. Now we go on and verify some more properties of the tensor products. And first among these is that the tensor product of any two modules is commutative up to isomorphism. So you have this proposition. So let M and N be A modules. M and N be A modules. Then there is a unique isomorphism. Then there is a unique isomorphism which map which sends this M tensor product N over A isomorphic to N tensor product M over A, extending the following map on generators. Extending the following map on generators. So the map from generators to generators is this one. X tensor Y goes to Y tensor X, where X is in M, Y is in N. So we just have to show that these tensor products are isomorphic via this map on generators. Okay. Now see the proof of this proposition. So proof so define a mapping, define F from M cross N to N tensor product M over A by, you define it as F of X Y equal to Y tensor X, where X is in M, Y is in N. Then this mapping F is bilinear. Then by the properties of monomial tensors, now then by the properties of tensors, if I take F of AX1 plus BX2 comma Y, by definition it is Y tensor ax1 plus bx2. But one of the properties of tensor says that it is y tensor ax1 plus y tensor bx2, which is again equal to a times y tensor x1 plus b times y tensor x2, and which is equal to a of f of x1 comma y plus b of f of x2 comma y. So f is linear in the first variable. So f is linear in the first variable. Now similarly, f is seen as linear in the second variable. So this is an exercise, do it, that f is linear in the second. So thus f is bilinear. So thus f is bilinear. So you have here m cross n to this n tensor product m over a. You have this f as bilinear. And from here to here, since this is the tensor product, say that bilinear map is J, say G. So by the definition of by the defining property of the tensor product, there exists a unique homomorphism, say H. So which makes this diagram commute. So by defining property of M tensor product n over A, there exists a unique homomorphism H, which makes the diagram commute. Which makes the diagram commute. Which makes the diagram commute. Means H composition G, that is H composition G is F. So this means for all x in M, y in N, H composition G of x comma y equals f of x comma y, and f of x comma y is by definition y tensor x. So this means h of g of x comma y is y tensor x, but g of x comma y here is x tensor y. So under g x comma y goes to x tensor y. We know this. So this means h of x tensor y is y tensor x. H of x tensor y is y tensor x. So on generators, this h is defined in this fashion. Now what do you do here? You interchange the roles of n and m in this diagram. You get a similar homomorphism from here to here. but with the property that it would send any y tensor x to x tensor y. Now interchanging the roles of m and n, we find a unique homomorphism k from n tensor product m to m tensor product n, such that k of y tensor x is x tensor y for all y in n, x in m. Now if you compose these two maps, hence k composition h of any x tensor y, which is k of y tensor x, and which is x tensor y. So this means what? This k composition h is identity on generators. So this means k composition h fixes the monomial tensors, the generators. Fixes the generators. So this means this k composition h. So therefore it fixes every element of the this tensor product m tensor product n. Once it fixes generator, it fixes every element. So therefore it is the identity map. So k composition h is actually what? Identity mapping on m tensor product n. And similarly, by similar argument, h composition k is identity on n tensor product m. So h and k are mutually inverse isomorphisms, and hence, so this means h and k are mutually inverse isomorphisms. So this means our job is done. So we have shown that m tensor product n is isomorph to n tensor product n. Okay. So this this isomorphism H, which is defined on generators, can be extended to the whole module. So therefore you have this proposition is true. Okay. So now we also have some more properties that so I will leave this theorem for the students to write its proof. This theorem. Let m comma n comma p be a modules, then there exist unique isomorphisms. There exist unique isomorphisms first one is that from this m tensor product n tensor product p to m tensor product n tensor product p to this M tensor product N tensor product P. This one. So once you have the isomorphism, you will see that. So therefore, you can say that the tensor product is associative up to isomorphism. And secondly, you will see that the direct sum distributes over the tensor product. M direct sum N tensor product P, it is isomorphic to this M tensor product P direct sum N tensor product P. So how do we define the isomorphisms on the generators respectively in this fashion? In the first case, the isomorphism, so X tensor Y tensor Z goes to X tensor Y tensor Z, and it goes to X tensor Y tensor Z. Okay, and secondly, X comma Y tensor Z goes to X tensor Z comma Y tensor Z. Now show that these maps are isomorphisms. Okay, so you have to apply a similar argument that we used in this theorem, this previous proposition. Okay, so I leave for you as an exercise. So do it. So I think I will stop this lecture. If you have questions, you can ask questions. So who will take the attendance? CR is there? Attendance कौन लेगा?
सर ली मैंने.
So you send it to me. Okay.
ओके सर.
हाँ, इनको करो भाई, जो एक्सरसाइज मैंने छोड़ दिए हैं इनको करिए सब है. ओके है.